Alright guys, in this video we're going to look at some basic antiderivatives. So what is an antiderivative? Well, it deals with working backwards from a derivative, right? So it's an antiderivative. So if we're talking about something like y equals 2x, we know its derivative is equal to 2. So this idea of working backwards means we're going to use an integral, just like we saw with before when we looked at definite integrals. Alright, but here we are not going to use any bounds. Alright, when we don't use bounds, we're actually looking at what we call indefinite integration. Alright, so this is your integration without bounds. Alright, so there's no bounds. Okay, so we're just strictly looking at the equation or the function, which is 2. Alright, we're looking to integrate that, so that means we are working backwards. Now the dx, just like before, means our independent variable is x. So x is our variable of interest here in the problem, and so when we work backwards we know the answer was 2x, but then we need a plus c, and this plus c we call the constant of integration. Okay, it's any number. Okay, so if we were to take the derivative of 2x plus 5, we know it would just be 2. If we took the derivative of 2x minus 6.8, we know the derivative would just be 2, right? So any constant there, okay, we know the derivative of a constant just goes to 0. So the plus c we put on the end there when we are talking about an indefinite integral. We don't bother with it when we are doing definite integrals, because definite integrals deal with area. Okay, so let's look at some other basic rules. Okay, first general rule: if we are integrating a constant, which we're calling k, then when we just saw an example of this before, it's just going to be k times x and then plus c. Okay, next one here is the power rule for integrals. So here we are looking at x raised to some power. So this is where we are going to reverse the power rule of derivatives. So recall the power rule for derivatives involved multiplying down and then subtracting 1. So if we reverse that, the opposite of multiplying and subtracting would be to divide and to add. Right? Remember how we subtracted 1? Now we're adding 1. Instead of multiplying, we're dividing. So some quick examples here. If we are looking to integrate x squared dx, okay, this is going to be x cubed over 3, all right, and then plus c, which by the way, we sometimes write this as 1/3 x cubed plus c. Okay, so you're simply going to add 1 to the power and then divide by that new power. So call that example A. Example B, sometimes you're going to have some prep work to do, meaning you're going to have to do some algebra, use your knowledge of exponent rules and various things to get it into the form of x to some power. So in this case, radical x we know is x to the 1/2. Notice how I have not dropped my integral sign yet, nor have I dropped my dx. We're only going to drop those two pieces once we've applied our power rule, okay? So, or just a basic antiderivative rule. So in this case, our antiderivative rule is to add 1 and then divide by that new power. So we're going to have x raised to the 3/2 and then divided by 3/2. Well, we don't typically like to write it like that. All right, instead we're going to write it as 2/3 times x to the 3/2, right? So dividing by a fraction is the same as multiplying by its reciprocal, okay? One more quick example here. Suppose we are integrating 5 over x cubed, all right, with respect to x. Once again, we have to get this ready for the power rule, so we need to rewrite this as x to some power. Well, we can bring up this x cubed as x to the -3. That 5 in front, remember from our properties from last section, we know we can just carry that along for the ride or put it out in front of the integral, and really we're just focused on this x to the -3. So careful, it's not going to be x to the -4. we're adding 1, so that's going to bring it closer to 0, so that's going to be x to the negative 2 divided by that negative 2. Okay, so we can write this as negative 5 halves x to the negative 2 plus c, or if this is multiple choice, you're likely to see negative 5 over 2x squared plus c. Okay? Okay, next, number 3 here. If we are integrating 1 over x with respect to x, our antiderivative is going to be the natural log of x plus c. Well, hang on. How come we can't just do x to the negative 1? How come we, if I were to rewrite this 1 over x, we know it's really 1 over x to a power of 1. That's the same as x to the negative 1. If we were to try to do our power rule here, if I add 1 to negative 1, I'm going to get 0. And then if I divide by that 0, that's undefined, right? So that's a problem. That doesn't exist. So we need a special rule here, and that is it's the natural log of x. Recall that the derivative of the natural log of x was 1 over x. So it should make sense to you that if we are reversing it, we get ln of x. Next one's pretty quick and easy. If we are integrating e to the x with respect to x, we're going to get e to the x. Remember we said e for easy. Alright, the derivative of e to the x is e to the x. So working backwards, you still get the same thing. Finally, the last part of our basic antiderivatives that we're going to look at deal with trig functions. And by the way, notice that in all these examples so far that we're looking at, our inner function has just been a plain x. Okay. Later on, we'll get into more complicated integrals where it's not just a plain x. Maybe it's a 3x or it's a 3x squared. Okay. So now trig is the last part. Okay, finally, trig. Make sure you draw a heart like this and shade it in because I know this is your favorite. We all love trig. Alright, so there's there's 6 basic ones here we need to memorize. So, and this is, remember, ideal for flashcards. You want to make sure you're somehow creating a system to memorize all this stuff. Okay, flashcards would be ideal. So, if we integrate cosine, we get sine. If we integrate sine, we get negative cosine. If we integrate secant squared, we get tan. If we integrate secant times tan, we get secant. All right, and again, just work backwards, right? Do a derivative. We know the derivative of the secant was secant tan, right? So working backwards would be logical. The antiderivative, or the integral of cosecant squared, is negative cotangent. And then finally, when we integrate cosecant cotangent, we get negative cosecant. Okay, so these are the big 6 to keep in mind here. All right, and again, notice how the angle is just a plain x in all 6 of these. All right, we're keeping it very simple in the beginning. Bye-bye.